For decades, the foundation of computer science relied on a single structural assumption. Algorithms were designed for one processor, executing one instruction at a time. Because of this, an algorithm's efficiency was evaluated almost entirely by its mathematical step count, a metric known as Big O notation. If the math was optimized, the code was considered optimal, largely ignoring the physical hardware underneath. But processor clock speeds eventually hit a hard ceiling. Pushing more instructions through a single core generated too much heat and required too much power, slamming directly into the unbreakable limits of thermodynamics. To keep increasing performance, the hardware industry had to pivot. Instead of building faster single cores, manufacturers scaled outward, creating multi-core clusters and complex multiprocessor topologies. The hardware had evolved into massive parallel grids. Yet, our classical algorithms remained strictly linear, creating a severe architectural mismatch between how software was written and how machines actually operated. It is tempting to look at a multi-core system and make a simple assumption. If you throw 1,000 cores at a problem, it should finish 1,000 times faster. In reality, that kind of linear scaling is an illusion. When a program is divided across multiple cores, it encounters the friction of data dependencies. Processors are frequently forced to sit idle, waiting for another core to finish a prerequisite calculation. To manage this, hardware relies on specific execution topologies. Architectures like SIMD, single instruction multiple data, apply the exact same operation across many data points at once, while MIMD allows separate processors to run different instructions simultaneously. Both process data differently than a solitary CPU. This creates a modern engineering mandate. Software can't simply be recompiled for new hardware. We are entering an era where the logic of the algorithm itself must be re-evaluated to account for these parallel paths. In modern architecture, evaluating an algorithm by its raw mathematical operation count is insufficient. The ultimate metric of success is how well the code manages the communication overhead between cores. The theoretical speed limits of parallel computation were formally established by computer architect Jean Amdahl. Amdahl's law splits execution time into parallelizable and sequential blocks. Adding processors compresses the parallelizable portion, but the sequential block remains static. Plotted, this creates an asymptotic curve. The sequential block is an absolute bottleneck, permanently limiting total speedup. There is an alternative perspective known as Gustafson's law, which alters the premise. Instead of keeping the problem size fixed, Gustafson argued that as processor count increases, engineers scale up the size of the data being processed, which keeps processors busy. Amdahl's law exposes an unavoidable physics problem. You cannot parallelize a task if Step 2 requires the exact output of Step 1 to proceed. Consequently, deploying massive hardware clusters without first eliminating sequential bottlenecks in the software results in millions of dollars of wasted silicon. We can see how these structural dependencies destroy concurrency by examining a classic algorithm, bubble sort. Standard bubble sort is strictly linear, moving left to right, swapping out-of-order numbers. Assigning multiple processing threads to sort the same array simultaneously triggers a structural trap. Threads will inevitably attempt to grab overlapping pairs of numbers at the exact same time. To prevent data corruption during these collisions, the system introduces mutex locks. This mechanism forces one thread to freeze and wait while the other finishes its swap. This is known as lock contention. By forcing threads to wait, lock contention destroys the parallel advantage. Strict sequential dependencies make classical bubble sort structurally useless on a modern multiprocessor. This forces engineers to abandon the classic approach and use parallel native alternatives like enumeration sort. Instead of sequentially swapping items, enumeration sort calculates the final position of each element independently, allowing all cores to work simultaneously without colliding. An algorithm's theoretical mathematical efficiency in Big O notation is irrelevant if its internal dependencies choke the actual hardware execution. Removing these algorithmic bottlenecks requires an intimate understanding of how the hardware physically stores memory. In a shared address space model, often programmed using POSIX threads or p-threads, every processor core on the board looks at the exact same physical memory bank. The danger here is overlapping writes. Developers must manually code mutex locks to protect critical sections, ensuring only one thread can modify a specific variable. In contrast, distributed memory assigns a private bank to each processor node. In machines like the CM5 supercomputer, nodes do not share memory at all. Instead, they must deliberately broadcast packets of data to each other across a physical network, using a protocol like the Message Passing Interface, or MPI. Choosing between managing memory locks on a shared platform or passing messages across a distributed network determines the entire structural design of the algorithm. To see how engineers overcome these constraints, we look to the ultimate benchmark of parallel efficiency, dense matrix multiplication. If a system computes a massive matrix multiplication by constantly broadcasting the dataset from a central node, it triggers a severe communication bottleneck. Cannon's algorithm solves this by mapping math to the hardware's two-dimensional mesh topology. Two large matrices are divided and distributed across nodes. During preparation, rows and columns shift to align data. Once aligned, every node multiplies its local block and passes data to adjacent neighbors. This cycle repeats, calculating the entire matrix without ever congesting the network. The algorithm's data decomposition perfectly matches the physical wiring of the hardware mesh. True parallel optimization is achieved when the flow of the data precisely mimics the physical geometry of the machine executing it. Matrix multiplication relies on rigid, predictable data structures, but unstructured problems like navigating a massive network using a breadth-first search algorithm require a different approach. A sequential breadth-first search methodically checks one logical path at a time. It uses minimal processing power, but it is exceptionally slow. To accelerate this on parallel hardware, engineers utilize speculative execution. The algorithm aggressively branches down multiple unverified paths simultaneously. By flooding the search space, it strikes the target node much faster, immediately terminating all other expanding branches. This creates a unique paradox. The total time to solution drops significantly, but the raw computational work wasted on exploring the dead-end branches is vastly higher than it would have been using a sequential logic algorithm. Modern parallel engineering deliberately burns excess computational power. Wasting hardware cycles is now an acceptable cost if it buys back time. We have transitioned from the abstract mathematics of big O step counts to the friction-heavy realities of multi-core physics. Achieving speed at scale is now a rigorous balancing act. It requires carefully dividing the workload, minimizing network latency, and synchronizing shared memory. The practice of writing code has evolved into a discipline where abstract logic must account for the physical machine. To push software to its absolute performance limit, the programmer must think like a hardware architect, molding data structures to fit the machine's physical topology. The most elegant algorithm in the world will stall if it refuses to respect the physics of the processor running it.